Okay, so everyone, so welcome to the weekly seminar. So today is a great honor to have Professor Yang to give us a talk. So Professor Yang does not really need the introduction, so I skip the introduction. So he's currently from Hong Kong University of Science and Technology, and is currently Chief AI Officer in WeBank. So Professor Yang, thank you for coming, and please start your presentation. Thank you.
Okay, thank you, Ping. Hello, everybody. Very nice to meet you. I want to today I want to exchange with you some progress on federated machine learning. This is also a very hot area, a very necessary area in many areas. So I will divide my talk into parts. First, I will talk about federated learning background, some technical societal background, and then I will go into some interesting applications, including finance and medical. Okay, let's begin. So we know that AI is undergoing a major revolution together with deep learning and big data. But in many applications today, data are in fragmentation, in data silos, like the picture shows. So what we face is a choice, whether we have the option to combine the data into big data, like what ImageNet did for computer vision, or we have to seek new ways to extract the value from the data, that is the knowledge, and create our models. After all, models are what we need in order to make use of these scattered data. So our primary purpose is not to obtain the data, not even to own the data, but to obtain a good model. So with this purpose in mind, our strategy will become clear. That is to seek a new way to take the data as input and create a global or unified model for future use without taking the data out of their local site. Okay, so this is a very brief summary of federated learning. So as I mentioned, the background actually is made by society. There are several issues. One is the legal requirement for making use of data. Constraints are getting more and more strict, like the GDPR in Europe, like the CCPA in US, and the cybersecurity law and data law in China. So the picture here shows where these laws are enacted. As we can see, it's spreading across the world. Okay, so this is one thing. Another thing is data itself actually has a lot of private information that society are getting more alerted, like the incident from Cambridge Analytica, and the subsequent laws across the world and reports, news reports such as happened to Facebook, Google, Microsoft, and so on. There are numerous other reports. So society is more alerted. Another dimension is the value in the data is actually is a issue, is a serious issue, in the sense that in big data area, people used to take the analogy that data is like oil, it's like gas, but in fact, data is different from gas. Okay, because data can be copied, but gas and oil cannot be copied. If you copy the data, the value of the data drops dramatically. So therefore, organizations do not want to share their data with others. because for fear of loss of value. And so this is another issue. As a result, we have the term departmental wall. Okay, even in the same company, different departments have a invisible wall between them, so they cannot freely exchange, and this is one of the main reasons. So federated learning takes another view of this. Instead of confronting the data fragmentation head-on, it takes a alternative route, and that is if we take the analogy of raising a sheep from multiple grasslands. So here we have 3 sites. So this sheep, all we care is that this sheep grows. We don't care whether who has the grass. Okay. So instead of taking all the grass to where the sheep is, we can take the sheep to where the grass is. Thereby, the grass do not need to travel beyond their local site. Okay, so the sheep can grow, and the privacy of the local site can be preserved. Okay, so with this in mind, federated learning, as shown in the picture in the middle, can be seen as a way to build a global model without moving the data. Instead, the model itself can be grown by exchanging encrypted parameters between local models. So here we have cooperation A and cooperation B. They cannot exchange data directly, but when building their respective local models, model A and model B, by exchanging their encrypted parameters, the global model, that is the federated model, can grow. Okay, so we list the scenarios on the left and also the synonyms on the left. So sometimes it's called collaboration among edge devices, organizations, departments, and sometimes it's called collaborative machine learning or collaborative distributed machine learning, and privacy preserving machine learning, multi-party learning, and so on. All right, so we wrote a book called Federated Learning, both in Chinese and in English. And in this book, we summarize some key ingredients. So the first ingredient is model itself. The model can be any model that we have studied in the past, such as deep models or tree models. A second component is distributed learning. In traditional distributed learning, there's no such concept as parameter or data protection. The main objective is efficiency and data balancing. But here we have to worry about heterogeneity, privacy, security, and model protection. Okay, so this is, and the third part is communication part. Instead of like the traditional distributed learning, federated learning has to worry about communication across organizations, how to minimize the cross-organizational communication and maximize the intra-organizational communication is an issue. Security and privacy mainly borrows from encryption and computer theory, such as homomorphic encryption, differential privacy, secure multi-party computation, and so on. And finally, there's the issue of incentive mechanism. That is how to encourage parties to participate in the ecosystem in order to build a model together. How do you evaluate the value of each participating party in order to distribute the profits among them in a fair and transparent way? Okay, so we can see a schematic for federated learning systems. And these issues, such as how to partition the data, there's the topic of horizontal partitioning, vertical partitioning, and so on. How do we introduce machine learning models? Can machine learning models be different among different sites? Whether we can take the scale of the federation to public or remain private. How do we engineer communication architecture so that the communication is centralized or distributed? How do we ensure privacy and security? And how do we ensure that each party is highly motivated to continue participating and to contribute more resources? Okay, so in the architectural viewpoint, we can see several key components in this way. First of all, on the top, we have an architecture for whether we organize the data in a horizontal way, that is, whether we partition the data by samples, or in a vertical way, that is, whether we partition the data by features, or by through transfer learning, that is, we need to build a private personal model on each site, where by exchanging their model knowledge, they can build a global and invariant knowledge across different sites. So this accommodates heterogeneous data distribution. On the next level, we have the issue of how to optimize cross-site communication, how to build incentive mechanism, and how to ensure security by preventing any information leakage. At an even lower level, we have to worry about any participating parties being a malicious party, or even a curious but semi-malicious party, how to build a defense mechanism to against model or data poisoning attacks. Okay, so these are, as you can see, truly multidisciplinary. As an example, we took AdaBoost or XGBoost algorithm and built a federated learning version of it. On the left is a schematic for the vertical version. That is, we assume the data is partitioned by features across different sites, and yet we can build a decision forest model. Okay, on the right hand side is a partition among samples, and here we can build a federated learning model across different sites by boosting. So adding it together, we can see federated learning is a very rich research area. So when you walk into a session, this session can discuss security, safety, efficiency, applications, or incentives, or any of these combinations of these. Okay, now talking about incentives, the issue is this. Suppose we have different data silos on the left. Each data silo is a party, and it has to choose which federated learning ecosystem to join. So suppose we have two of these systems to choose from. Now, there has to be a mechanism to evaluate either using a sandbox or some testing cross-validation period to allow the model to be built and a test to be enacted in order to obtain the profits. And this enables the data participating party to choose between different ecosystems. And if we make it right, then the winning one should be one guided by game theory, by economic theory. Okay, now, so that was the technical part. As for applications, in a very short amount of time, in the space of 3 or 4 years, we have seen a dramatic growth of blossoming of application areas, such as computer vision, natural language processing, recommender systems, and in different industry sectors such as finance, insurance, healthcare, education, IoT, smart city applications, edge computing, and so on and so forth, and even satellite technology using 6G. Starters always wonder whether there are public data sets. There are. So there are some data sets listed here. One data set is in the Fed Vision data set, and they cover the street monitoring using cameras. And the goal is to build a horizontal federated learning system that is able to do object detection by taking across different cameras. In CMU, there's a data set called LEAF, and this data set allows a benchmarking data set for federated learning. And there are data sets available in USC by Chaoyang He and group under the open source system called FedML. There are also many open source platforms such as Fate, which is a open source as well as a enterprise level federated learning system. Google has a system called TensorFlow Federated, and there are many others such as Baidu's PedoPedo, which is also a famous system. So if you want to study federated learning, you have to know something about secure multi-party computation and encryption, decryption methods. And so here I give a very brief overview of these. So MPC is a technology that has grown from very early on in computer science. Its best part is it can, for every algorithm it proposes also provides a security proof in a well-defined simulation framework. It guarantees zero knowledge among different parties, and yet full cooperation in terms of the basic polynomial and beyond mathematical operations. Its drawback includes very expensive communication. So the communication back and forth usually is very heavy duty. It is said that if you use MPC directly to do model building between two parties, the efficiency can be 10,000 times lower than a centralized version. 10,000 times is something industry strength cannot survive. So as a result, MPC has mainly remained in laboratories so far, although there are some initiatives in combining hardware and software in order to speed it up. Professor Andrew Yao is a pioneer in this area with a famous garbled circuit protocol. It allows complete zero knowledge between different parties, such as the famous millionaires problem, by following a sequence of algorithms, allowing the so-called OT, oblivious transfer of information between different parties, enable the final computation to be exactly correct, and yet no information is leaked. In contrast, in machine learning, we usually do not need exact computation. We actually, most of the model building can survive with approximate solutions, such as probabilistic solutions. So we can relax a lot of these requirements. There are examples that people can check in, such as early as 2017, there is a very foundational work called Secure ML. It uses linear regression, logistic regression, and neural network training by using only MPC and secret sharing between different parties. Okay, so parties can be completely untrusted, and yet they can build a global model between themselves. This work is not used in practice in industry because of the computational expensiveness. There's also a large body of work on differential privacy. Differential privacy is the work that started by Dork in 2008, and since then there has been a dramatic blossoming of research in this area. Its best part is by introducing noise on the data, you can actually open up the data API by obscuring individuals in your own data. And this is guaranteed by a probabilistic proof, such as you can have an epsilon delta proof, which is loved by mathematicians. The only drawback of this is there are two dimensions. One is efficiency, effectiveness. If you introduce noise into the API, although you can obscure individual's identity, you also introduce ineffectiveness in the model. So the model becomes less accurate. And this is usually not allowed in these very serious commercial competitions, such as recommendation, advertisement, or even finance in credit rating. Okay, so this is a big issue. Another big issue is it doesn't prevent data from being leaked. With 1 minus epsilon probability, there's also a possibility of data being leaked. This is not tolerated in any commercial applications. In commercial applications, the IT department has to have the guarantee that there's no data that is leaked at all. So it doesn't solve this problem. As a result, differential privacy has been only adopted by a few applications in industry. Homomorphic encryption is an encryption method that allows preservation of mathematical operations, such as polynomial operations. These algebraic operations can be performed by distribution law, such as addition, right? If you take two encrypted packets, the result is to do the addition on the contents and then put a secure packet around it. And so this allows models to be updated and computed without looking a peek into the contents. So it's a good way to protect the parameters and data. Although it's highly recommended not to use this method directly on the data. So people are using this on parameter protection, so that different global model and local model can sync based on some encrypted model parameters. Now, a big drawback of this is inefficiency. Although algorithmic progress has been very rapid, together with hardware progress to support efficient HE, homomorphic encryption is shorthand is HE. So with this method, then some nonlinear, non-polynomial computations can also be done. So for example, we can use a piecemeal approximation to a nonlinear such as sigmoid function, as shown on the right, and use some expansion such as Taylor series or even more sophisticated expansion, polynomial expansion to and then apply HE to enable some machine learning requirements. So in order to highlight the need for protecting parameters, here is an example, and it's even more highlighted by a 2019 NeurIPS best paper by an MIT group. It's called Deep Leak, this work. So the idea is if two parties are communicating with each other only using differential privacy, then it's still possible. So the differential privacy is protecting the sharing of parameters between the two parties. It's still possible for any party to reconstruct the original data on the other party, as long as you don't introduce enough noise on the parameter protection. But if you introduce too much of the parameter protection by the noise, then it defeats the purpose of this collaboration because the model becomes too inaccurate. And so this creates a dilemma. So this highlights the necessity of using something like homomorphic encryption and MPC when using this, when we compute the global model. Okay, now, earlier I mentioned in the architecture, there's such concepts as horizontal, vertical, and so on. So let me show a graphic view of what horizontal is. Suppose we are a mobile phone company. So we are interested in updating some AI models such as language model, some N-gram model, or even computer vision model in a server, right? Using the data that's constantly being collected in each edge device. So this becomes a client-server architecture. Now, so this architecture corresponds to each edge device has a collection of samples, and multiple edge devices put together has the whole view. Okay, each one only has some samples. On the other hand, all the edge devices are very similar to each other, so they are collecting similar data in terms of features. So they share features, they share a column, but they have different roles. And so we call this horizontal because the partition is partitioned by horizontal. So on the right here, we have data from A, data from B, and maybe there are some right. So there are some feature sharing which allows you to build a common model between them. And building this common model is the goal for horizontal federated learning. Okay, and so there are a number of steps which I won't go through very much detail. The idea is each client device is communicating its model parameters with a coordinator, with the server, and the server will do a federated averaging so it's a kind of bagging. Okay, so if you're into boosting and bagging, it's a federated bagging using homomorphic encryption, and then distribute the updated model among edge devices. So this repeats forever. So the research issue then becomes which edge device do we choose in order for the model performance to be the best? How do we take a updated global model locally and personalize that model using the local data? How do we build a global federated averaging model by admitting that the local edge devices are heterogeneous, either by features or by distribution of the X dimension, or by a combination of that? how do we prevent any edge device to be a bad guy, okay, to be a malicious user? How do we do that? So these are research issues that are currently hot research areas. So if there are PhD students in audience, you may take note. So this is the grandfather paper, the Google paper for Android model updating. The federated averaging is occurring here in the cloud, and each computing device is an edge device. Now, so my team took this idea and developed the vertical dimension. So the idea is if you have a bank and an internet company and they want to collaborate, usually it's the case that they share a lot of samples, like this red area, but they don't share a lot of features because, you know, a bank is interested in financial transactions, whereas a internet company is interested in clicks and in contents. Okay. Now, by collaborating, they can build a better user model and therefore a more accurate credit rating model for the bank or a better behavior model for the internet company. And so this corresponds to partitioning the data among the feature dimension in a vertical way. So this is called vertical federated learning. Now, compared to horizontal, vertical is more like between organizations, whereas horizontal is between consumers. Okay, so this is the bank example. So we have a retail company and a bank, and they share from U1 to U4 the user IDs. And so when they build a model, they have to have a set of common users in order to expand their dimensions vertically. And so the question is, how do they verify each other's data in order to find the cross intersection of the data without revealing the users that they own, but the other parties don't own? Okay, so I have some users. User names are very, very valuable to me. I only want to share with you only those data that we both share. But for those data that I have, but you don't, I don't want to let you know. How do you do that? So this can be done using, so this is known as entity match, okay? So this, we can build different algorithms using multi-party computation or using homomorphic encryption to find the intersection. And I think this area can be a very rich area for research in the future, because this kind of operation is very widespread among parties that collaborate with each other. Okay, now back into model building. Suppose we can find the set of common IDs. The next issue is, how do we, under a vertical federated learning setting, how do we build a global model? And the idea is to go through these 4 steps as shown on the right. So first they send public key to each other, and then they exchange intermediate parameters and loss information. Parameters are gradient information. And these information are encrypted using homomorphic encryption. So that's why public key and private key becomes important. And so by computing their own gradient and loss information, using both their local information in the last iteration and the exchanged information under homomorphic encryption, they update their model. They update their model, and then they go through the next round by exchanging keys and so on. So this global model is built virtually in the sense that party A has a local model, model A. Party B has a local model, model B, and they both are respectively growing. Okay, by putting them together, you have a global model. And so once you have the model built, then you can use it for inference. Okay, that is when a new user comes, you want to ensure that this part of the result is computed in party A, part of the result is computed in party B. Again, the information exchange between the two parties allow each model to progress steps before reaching a final decision. Okay, and finally, this result, which is what we call label, right, or Y dimension, is computed in one of the parties, say party B. Now, going through all this, you have to at least give a security analysis to show that in model building process and in inference process, no information is leaked, including the new user at inference time and including the respective data in the model building time. And so at least for academic publications, if you publish a new federated learning algorithm, the minimal requirement is you provide a security analysis. Although if you take to the industry, if you give some kind of IT manager the security analysis, they still cannot be ensured that the systems are completely secure. They have to have some kind of insurance, legal backup, as well as some regulations from regulators that allows you to use this setting. So that is why we have a part of our team is working with governments and legal and also regulators on law enacting and drafting. Federated learning is not just on the algorithm and technical side. There's also a societal and governance side of the issue. So that is why it's not purely a university research issue, and that's also my motivation to work on this in a industry setting. Okay, so I mentioned XGBoost and how you can take this and build a federated learning version. In fact, students can take almost any algorithm in a machine learning book, in the table of contents, and build a federated learning version of it, and still has a chance to publish. So this area still has a lot of low-hanging fruits, and so this is good news for students. I actually tell my team not to work on every version, give other people a chance. So we are very happy to see the number of papers published in this area has been dramatically growing. Like in 2018, we counted the Google Scholar federated learning papers. There are like 20 or 30, but today there's several thousand. Now, sometimes you have two parties, their data are different in terms of distributions or different in terms of features. In this case, and sometimes the goal is not just to build a global model and use that for inference, but instead use the model for local purposes, such as, if you use TikTok, if the model comes from the server, you still are not satisfied because its recommendation is based on public interest, but you want the model to be built on your own interest, your own past history. So in order to do this, you have to do one extra step, that is transfer learning locally, okay? To take a global model using your local data and do a transfer learning from global to local. And so this architecture is shown at the bottom, where we show how to do this transfer learning using, assuming that we have a deep model on each site, and they are using vertical, that is the feature dimension partition between the two parties, and by exchanging information and by working on the model building in a transferred common space. Okay, so people interested in this can visit a classic transfer learning paper called Transfer Component Analysis, TCA, like principal component. Transfer learning also has its own transfer component, which allows subspace to be built where transfer can happen, even though the original spaces have different distributions and different features. So this can be done on vertical. The picture here shows vertical, but you can easily do that in horizontal. I think I've seen some papers more or less in this area, but you can build a very rich body of work. Again, for PhD students, this is a very low-hanging fruit. How to combine transfer learning to enable secure, federated, and also heterogeneous model building between horizontal sites. Okay, so federated transfer learning, I mentioned it already. People always complain about the inefficiency usually introduced by two parts. One is the need to communicate between parties. Usually the internet is much slower than the intranet. Okay, not to mention secure internet, which uses some kind of encryption. Now, it is estimated today in industry, if we build a ecosystem, several participating parties building a global model and using the global model for inference, usually you expect a 50 time to 100 time slowdown as compared to a centralized version. 100 times slowdown is intolerable. Although if you are 100 times slower than centralized, if you are 100 times slower in training time, it's still tolerable, but in inference time, it's absolutely not. Okay, so people are using this method, using this as a new challenge in building hardware solution and software solution. In hardware solution, we have heard Intel and NVIDIA are respectively building their own hardware solution to speed up federated learning. So soon we will see custom-made chips to enable federated learning in the market. And in software solution, here is an attempt in which our team built a system called batch crypt. It encourages batch computation between multiple parties, allowing homomorphic encryption to happen between these parties where the inter-communication is minimized by maximizing the intra-communication within each site. And so the result is an acceleration by 20 to 100 times, which is very encouraging. Although this hasn't been fully deployed, we are putting it in our system called Fate. It's an open source software. Now we move our attention to another direction, which is incentive building. Incentive building is increasingly required by people in the market. It's not just an academic issue like motivating economic or game theory or multi-agent Amos community to work in this, but also actually a customer requirement from the market. People are asking, like in different hospitals, the hospital head are asking, why should I integrate my data with other hospitals? So what if the global model is more accurate? How does it benefit my people? Okay, so this issue becomes very, very intensive. So the issue itself is if a data party, a data owner joins an ecosystem, how do you evaluate the proceed from this participation among different parties. This can be seen as revenue, which is cash, or it can be esteem in the community, or it can be impact in terms of in terms of work. So although we use a dollar sign, the dollar sign can be realized by some kind of benefit, some form. So this work has just started, and we hope to see a first deployment of it in the market. Although in finance, the requirement usually is by law. So by participating in this form, they conform to some kind of financial government regulators. They say that if you obtain your credit rating information for your loan issuing or for your banking operation for security, if you follow a federated learning paradigm, then we consider you as obeying the law. If otherwise, if you just exchange data with other parties, then it's against the data law. So this is a motivation by the whip rather than by the carrot. And it's already happening in finance. But in hospitals, it's not the case. So we are still looking for ways. Okay, so how to incentivize people to join. If you want to, so our review of technical part ends here. Before we go into applications, by reviewing some typical cases, I should point you to a very good survey paper in this area, which is led by Google, but joined by many people, including ourselves. You can see my name here. Now it's called Advances and Open Problems in Federated Learning, and it's available on archive. So people want to know more can visit it here. Okay, so applications actually grow very fast because this work is done. I think the most innovative work, at least the first wave, is done in the industry rather than academia. So this is very different from things like deep learning and other computer science concepts, such as encryption and so on. Rather than led by professors, the work is led by industry. One such industry is, of course, the mobile phone industry, right? Like Google's Fed averaging. Another one, the vertical federated learning is motivated by finance, fintech. And here we have, among fintech, we have engineered deployed applications include, so this is led by my team in VBank. Anti-money laundering, you can see the increase in recall and accuracy. In internet banking risk modeling, this is the key component of all banking. In internet and insurance, in reinsurance especially, increasing the coverage ratio and personal insurance. And internet and retailers, such as the online shopping, in improving the accuracy of online shopping. Okay, so here's a example of risk management. So here we have a on the left-hand side, we have a company which modernizes or digitizes receipts for almost a very large sector of industry in China. So they have the most complete receipt information. This information also provides valuable company health information, okay, whether a company is healthy. And it can be used by banks to build a credit information. Banks are interested in whether a loan applicant will suffer from a delay in payment and the probability of such event. But the data cannot be exchanged because they are very private and by law they cannot be exchanged. So how do we build a global model by making use of the data that's located on each site? And so here we use vertical federated learning, and as a result, the loan application is dramatically improved. I should tell you that WeBank is an internet-only bank. It's one of the first such banks in the world. It only lives on mobile phone. Okay, it's a mobile phone only bank. So therefore, all the applications are answered in microseconds. So that means there's no paper application, there's no face-to-face application, and yet the error rate or the bad loan rate, default rate, is 1/10 of the average such rate in the market. Okay, and the reason for doing this is federated learning. It has more than 100 participating parties in order for it to build a very powerful and effective and efficient credit rating system. So now WeBank is covering 300 million individual users and 3 million micro and small size businesses in China. In computer vision area, we have a deployed system working with a company called Extreme Vision in Shenzhen. Their job is to make every camera on site intelligent, so they can recognize some unsafe behavior in the construction sites, such as fire and such as, you know, if a worker didn't wear a helmet, it can detect that. But each construction site only has very limited knowledge, data. So by connecting them together, it can build such a more powerful model, more accurate model for construction site safety insurance. In recommendation systems, this is often used in online recommendation, in video recommendation, in product recommendation. Usually the idea is collaborative filtering, right? Now by allowing the parties to communicate with the server in a secure way, in federated way. So this is horizontal federated learning. We can build a more accurate model for the products. Or by allowing each party to communicate with each other, we can build a more accurate model on the user model or product model. So using this method, we have ensured advertisements and short videos to be recommended locally. So this is an example of personalized federated learning. Now, federated learning is also being used on voice recognition, speech recognition. So here we have different service centers, such as, you know, a service center for finance, for online banking, another service center for online retail. If they want to collaborate, they can collaborate their ASR, the speech model, okay, like language model and so on. They can do this by using federated learning and using transfer learning for their localization and increase their accuracy. Okay, and so this is our score sheet. So we have applied this for more than 2 years, and we have a federated learning system with almost 100 million level data processing in real time. So this allows real time credit rating scenarios such as anti-money laundering and credit rating. So we have served over 40 million such queries by using federated learning. In our ecosystem, there are 530 organizations, and we have 74 patents approved and 400 online to be approved. We have participated in 5 national level and international level standards and published several textbooks. We received AAAI Industry Award in 2020. Okay, so here's an example in anti-money laundering. So we have several banks in a horizontal federated learning setting because each bank has a different set of users. And together, they use vertical federated learning with the internet company because they share a lot of users but not features. And so this allows a more powerful method for global anti-money laundering system to be enacted. And it has been used by the central bank. For credit rating, so on the one hand, we have non-finance companies. On the other, we have finance companies. And WeBank serves as the coordinator to build, and this system is called Federated Data Network. So this blue line on the right shows the finance industry method called KS, and it increases with the introduction of more data sources. In the insurance, we collaborated with Swiss Re, which is a famous and very large-scale reinsurance company, and together with multiple insurance companies and internet company, we built a personalized insurance system, which increased the coverage by a lot. In recommendation system, we used it for our enterprise finance system. As I mentioned, we issued about 300 million individual users and 3 million company users. For the company users, we use this for federated recommendation system for advertisement system, which can be more accurate and more secure. So, for example, like ByteDance has its own team to apply federated learning on mobile and advertisement recommendation. In IoT applications, we use this for supply chain management in order for companies to do better inventory prediction, inventory capacity prediction for downstream and upstream prediction. And this has been used also in our enterprise loan setting. In federated edge computing, we are working on a prototype system to allow different autonomous driving companies to collaborate with each other without exchanging their sensitive data. And allowing different autonomous vehicles to collaborate with each other without transmitting their local data to the server. So the result is a system that not only allows better computer vision, but also allows better decisions using a federated reinforcement learning system. Because each party is like a AlphaGo. So we have a federation of AlphaGos all together. So each AlphaGo is playing a Go or chess, and together the federation can make a better global and more robust decision. As I mentioned, our IEEE standard was published in March this year. It's the first such international standard on federated learning. Following this work, we are going to publish a series of sector-specific, such as finance, education, and healthcare only standards for federated learning. Okay, so these are some standards within China, within the national level or international standard. Also, federated learning cannot be done without worrying about openness, because every party has to ensure that, number one, every participating party are using the same software system in order to communicate. On the other hand, they have to trust the code they are using. So as a result, we have to open source the software in order to ensure the best transparency. And our system Fate becomes the industry adopted, the most adopted open source software in the market. So in medical applications, we have a collaboration with Tianyan Lab in Tencent and applied it to several hospitals in Hubei, and on the topic of better stroke detection. Usually before a stroke patient in medical application, but before a serious stroke happens, there is a series of signs such as high blood pressure, such as people passing out, such as the diabetes and so on. So along the timeline from left to right, you can see any individual user has a series of signs. Maybe these signs are recorded in different hospitals. By working individually as a data silo, you have no way of detecting this stroke early. So, so our idea is using federated learning by piecing together all the individual evidences and build a global view. Okay, so this hopefully will allow better protection, better prediction. And so these records includes the disease, the symptoms, the annual checking, operations, and family history, and so on. And they're indeed located in different, so each triangle here represents a data silo. Okay, so we hope to use all of these to build the machine learning model as shown in the middle. And the data are taken from 2017 in half a year. And so following the standard model training and prediction and inference phases. And so the task is to partitioning the user into different levels of seriousness from 1 to 10. The result is very encouraging. For example, for some banks, for some hospitals with only a small amount of data, the increase in detection rate is as high as 20% in terms of AOC. Even though the hospitals have different numbers of samples, such as shown on the lower left, some has as many as 130,000, some has only 11,000. Even so, we can build a global model taking advantage of the heterogeneous data. Okay, and the result was published in Ichkai workshop paper. Another example is in drug discovery. And this was a recent work published led by Professor Qi Liu from Tongji University. His lab works closely with a number of drug discovery companies in China. And in this particular example, he works on a compound composition known as QSAR. Okay, so by using the QSAR data located in different parties and building a horizontal federated learning system, so the team has built a global model that's more robust and secure. And in this case, we see a diagram of three parties working together on their local models. And so it's simulated on some famous simulation data in the market, and the result is presented here respectively in balanced and imbalanced cases. No matter what cases you deal with, the result is more robust than before. Okay, so the conclusion is this prototype shows horizontal federated learning when used in drug discovery is very effective, and it's also the first such case internationally. Finally, I want to quickly go through some challenges in federated learning. Here I want to point out some very famous papers in this area. Like in 2018, there's a paper titled "How to Backdoor Federated Learning." So the idea is even if you use differential privacy among different parties, you can still leak information out. Another one is called deep models under the GAN information leakage from collaborative deep learning. This is how to use GAN to simulate in a horizontal federated learning setting in order to learn secrets among other parties. Another issue is how to use AutoML on federated learning in order to reduce the reliance on engineering teams. So if a party is a finance company wants to deploy federated learning but doesn't have such expertise on parameter tuning, it can use a automatic federated learning framework that we developed called AutoFL, and also the University of Southern California team also developed a AutoFL version. So it's a very active area of research. I mentioned earlier MIT has a research team on model compression, and this team in 2019 NeurIPS published a paper called Deep Leak, showing that if you use differential privacy among parties and not careful enough, you can leak information. But if you use too much noise for data protection, then the model becomes rendered completely useless. So this gives us an idea of how to draw the best balance between model protection and the effectiveness. And so there's a series of work coming out in this area. So to conclude, there's a large number of references. I give them out here, and Professor Li Ping can share this information with if you're interested. But on the market, there are several books, like our recently published book called Practicing Federated Learning, based on our open source software called Fate. We walk a beginner through step by step on building your own federated learning system, and also provided a system. So here you may be wondering why it uses the impressionist picture. In fact, this is a real picture using transfer learning to transfer into a impressionist style. So this shows that transfer learning and the federated learning working together can solve a lot of practical problems. And the main character in this picture is sheep. So this takes the story of the sheep grazing among different sites in federated learning. So I welcome questions if our time allows, but otherwise my talk ends here. Thank you all for listening.
Thank you, Professor Yang. This is great. There was a lot of great details and lots of information for further research. And yeah, so there is a question. I wonder if the guy is Chen is still there. Hey, Chen, are still there? Yeah. Otherwise, I'll let others.
Yeah, I'm here. Yeah, I'm here.
Oh, okay. Okay, yeah, you can ask your question.
Yeah, I got two questions. I have loaded them in the message. The first one is, in the meeting scenario, we have different mobile phones, computers linked together one network. In order to protect in order to train the model for audio like ISR, noise cancellation, and other audio improvement. Lots of audio or voice data we needed, but to protect the privacy of the meeting of the participants and protect the meeting content. Is there any practice or success experience on this area? This is the first question. Yeah. And
okay,
the second,
so let me answer this. Yeah. So ASR using language model to build a global model and then to transfer the global model for personalization has been applied to our call center scenarios very successfully. For example, we can have a more robust model by using federated learning by collaborating, or we can personalize this kind of model for different tasks in finance. For example, in one track is about savings, another track about loan application. But in a meeting setting, we haven't tried it, especially in real-time speech recognition. So it's an interesting application. I think if you are thinking of using it, by all means, I'm very curious of the result.
okay, thank you. There's another question. Recently, I have seen some research work from Navida. It's about the security of the federated learning. The researcher used like a non-privacy data to recover the original image, just like you showed the paper 2019. The paper is, I also write down in the message, it's called the see-through gradients image batch recovery while grade inversion. Yeah, it's also be accepted by the CVPR 2021. Yeah, so maybe you can talk something about the security or the of the federated learning about in this area. Yeah, it's like a balance. It's just like you say.
Right. I have to look into the paper in detail, especially into how the encryption method or whether differential privacy is used, because when people are saying gradient leakage, they usually mean differential privacy. So I have to look in the detail here. But in general, the reason why some people are attacking differential privacy is, as I said, number one, the noise introduces error. Number two, it's not completely secure, even for gradient sharing. For homomorphic encryption, if you use that, the drawback is efficiency, but the advantage is increased security. There's a added area of insecurity, which is even if you use homomorphic encryption and you give unlimited amount of time for two parties to exchange gradient information, it's still possible for the other party to engineer a system such as GAN or such as an adversarial network to guess your model parameters. We are working on this currently.
Okay, thank you, Professor Yang.
Thank you.
Thank you. There are a couple of raising hands. Yeah. The first one is Mr.
Yeah. Okay. So thank you for the wonderful talk, Prof. I also have a couple of questions because this is very new field for me. So I'm still trying to study the basics. Like the first question is, I know by de facto that it seems from your presentation also that most of the applications are based on horizontal learning, federated learning, like several of the examples that you gave. So can you please give some examples where vertical federated learning model can be really applied, or what are the basic requirements for deciding which of the two federated learning approaches will be more useful?
Very good question. Thank you. Horizontal is more often used in mobile devices. such as, you know, a mobile phone company has a server and has many clients. Each individual phone is a client. On the other hand, in cross-organization, we call it B2B application, business-to-business application. It's more often the case that the model is vertical. Such as in our application, we have served hundreds of finance companies and non-finance companies. Their model is vertical. One example is we have a very large internet company working with us. They cannot exchange data, but we are interested in boosting our credit rating information further. But we don't have that many user dimensions because after all, it's a finance company. But internet companies, they have many services. So the user behavior information is very rich, but they don't have any finance information. So by putting them together in a vertical way, suddenly the model performance is dramatically increased and surpassing any in the market. So this kind of finance application, also in hospital application, if two hospitals are specializing in different testing methods, such as one on the DNA testing, another on the MRI testing, then they can work together by building a more fuller picture of a patient in order to provide the service. So both are needed, but one is more in the business to business, another is more on the consumer to consumer.
Thank you very much for that clarification. And the second question is, before now I've worked on recommendation systems, and I used to know that cold start problem is a very strong issue in this kind of research. So in federated learning, how is the issue of cold start problem resolved at the initial level?
Can you repeat the term you used for the problem?
I mean, cold start issue.
Oh, cold start. Oh, okay, right. In recommendation system, when you go to a new area, there's very little data.
Exactly.
Yeah. Yes. In this area, you have two issues. One is a transfer learning issue. You have to find a rich domain where you can build a pre-trained model, and then you take that model and apply it locally in order to give a boost to solve the cold start problem. So number one issue is a transfer learning. But in transfer learning, you should also protect the privacy and security of each party. So we have a source and a target. So the source wants to protect the source data. The target wants to protect the target data. And also, by exporting the pre-trained model to the target, the source is interested in protecting its own parameters, certain parameters. It cannot be shared with the target. So this issue of transfer learning, along with model and data protection, is a very interesting federated learning problem.
Thank you very much, Prof. Please, is there any particular book you can share on this specific problem?
Yeah. We have some papers we can share. You can work through Professor Li Ping by sharing with you the references.
All right. Thank you very much, sir.
Thank you.
Hello, could I ask a question?
Yeah, please.
Hi, Professor Yang. I have a question about the vertical federal learning. So when you have an internet company and like WeBank together, they will train a model. So when they do the vertical federal learning, then they will have a party like the model in each of the party. So when they do the inference, it looks like they have to do inference together with the WeBank and the internet company. My question is, how could they do it like at the same time? So if WeBank want to do the inference, how could they let the internet company work with them?
In this case, there's a part model is is at VBank. Another part of the model is with the internet company. These two models have to be in sync. That is, they have to communicate in real time. So when new user comes, VBank first computes its first round, and then it requires some result which can only be computed by the internet company. In this case, it will send a request together with some encrypted new user information along with the packet. And so when the internet company receives that and receives part of the result from VBank, it will start its own computation, computing a partial information encrypted and sent to VBank. After several exchanges like this, eventually VBank will have the final result and will make a decision on the user. So all of this is done in real time. They have to be in sync.
Oh, so the internet company kind of have to provide the service.
That's right.
For VBank. Okay.
Yeah.
Thank you. I have another question. If when two parties they want to do the fair learning together, do they have the pre-knowledge about the data quantity the other parties?
They have some knowledge, but they don't have all the knowledge, especially the private knowledge.
Okay, so if one party actually poisons the model with some malicious data, so the other party maybe have no way to know. I mean, could they detect that?
Yeah, that's a very good question. So there has to be some testing periods. So we call them sandbox, in order to verify the truthfulness and the value of each participating party. Otherwise, the case that you mentioned can happen. So for example, in horizontal federated learning, a participating mobile phone, maybe its purpose is to introduce data so that it can bias the global model towards its own interest. It's possible to do that. And so it's so there's study currently on how to prevent that from happening.
Oh, okay. Thank you.
You're welcome.
I have two questions.
Yes.
Professor Yang, thanks for the wonderful talk. So in the beginning, you mentioned about the GDPR policy. And like one important requirement for that will be like to have the individual to have the right to have their data erased. So I'm wondering like if it's possible, say just someone like some device, some client contribute some data, and that after some time point, they want to delete their data. So like to be comply with the GDPR policy.
Yeah.
I'm wondering if you have any insight on this.
Right. Okay. So if you read GDPR policy carefully, you will notice that suppose the organization has built a model using your data, and then you send a request. Its requirement is that in future updates of the model, it cannot use your data, but it doesn't. It's not required to delete that model or edit that model to edit out your past data. Yeah, so this can be conformed.
Oh, okay. So then just in the future.
Future, correct.
Okay. I have another question regarding the collaborative fairness. So I'm just wondering if that's a concern or not. I'm not talking about the sensitive attributes, like in terms of fairness, but like say, like there are several like banks want to train a model, but one bank, such as WeBank, they contribute a lot of the data. So if we treat all the parties like equivalently, maybe then might not be a lot of incentive for like WeBank to participate into this model training.
Right. So you are absolutely right. This is an economic question. If one party is contributing way too much and not benefiting as much, then there's no incentive for this single party to continue participating. This is correct. So therefore, in our practice, we usually find different participating parties can contribute in one area that is not subsumed by others. Okay, so you have your own advantage. This is like building a student team to complete a term paper. If all you can do can be done by some other members in your team, then you probably will be kicked out. You have to provide something unique, only you can do. Yeah, so far we have been choosing our collaborators very carefully, and it hasn't happened. But you are right. Yeah, this thing can be formulated mathematically. I think that will make a very interesting multi-agent paper.
Yes, thanks.
Thank you, Yinjie. So Professor Yang committed an hour and a half for us, so it's almost time. But I will let maybe one person ask a question. Yeah, one more person.
Yeah. So Professor Li, so somebody has asked to share the slides. How about I send the slide to you, and
okay.
People can ask you because they know how to contact you. I have no problem sharing the whole slide with people. Yeah.
Hi, Professor. Fletcher, I think I'm guessing that you should be very tired and you devote so much time here. I'm trying to ask the last question for this talk. And my question is pretty personal and specific. So by the way, my name is Louis. I'm from the heterogeneous computing team. So I'm an intern here. I'm very interested and impressed by your last presented work related to the healthcare. I'm working with my school advisor on an emergency medical virtual assistant. And we have spent quite a lot of time to building up the whole pipeline to suggesting the emergency protocols or treatment to the victims. And but we are trying to make our contribution to system aspects, which should be like some papers devoted to ATC or parallel computing or edge computing papers. We are not trying to build in like the Chao Yang's framework level work, but we are trying to do system work. I'm just wondering if you know or you can suggest any specific system directions and that we can try, and which you can foresee that should be a good paper in the future. Yeah.
In medical area. I think any of your application must have some unique point, which is interesting. So along the technical dimension, in medical, like say emergency treatment, there's a lot of privacy information and security information as well. On the other hand, they have to share information in order. So let me take the example. Suppose you have 3 emergency vehicles. How do you distribute it properly in the whole city in order to cover potential future emergency situations? So this is a planning and scheduling problem, but it can be done by 3 data centers. Each center is covering its own area using a emergency vehicle, and they have to collaborate, the 3, in order not to overlap too much with each other. So this is in computer vision, in reinforcement learning. In each of these, you can build a federated learning system and to improve the global efficiency. I think this would be a very valuable thing in terms of applications and in terms of technical advance.
Okay, I see. Thanks for this suggestion. Yeah, thanks.
Thank you. Thank you all. The questions are very, very nice. I'm very sorry for my my late appearance. I hope I can compensate you by sharing the slides with you.
Thank you. No, it's more than an hour and a half. It's way more. It's much more than an hour and a half already. So yeah, if Professor Yang dedicate me to share the slides, I will have to do so too. Otherwise, it's for battle internal use only. But yeah, since yeah. Okay.
Yes, I appreciate it, Professor Lee. Most of us came from really far away and we're late in the night. So, it's hard to concentrate for the whole presentation. So sharing the slides with us will be so much helpful. Thank you so much.
Okay, thank you. Thank you, everyone. Yeah, let's thank the speaker one more time. Yeah. So Professor Yang, thank you.
Thank
yeah,
you.
Have a good day.
Thank you. Thank you.
Thank you all for participating. Thank you very much.
Thank you.
Bye now.